And this is the actual corollary of Lagrange interpolation that we'll use. Given that we have fixed points and all these points are integers, the polynomial that takes these values at these points can be expressed as follows, where Cij are rational numbers depending only on tO's. But how will this knowledge help us in computing the product of two given numbers? So recall that we have this expression, and now we can use the following trick. So we need to compute the product of two polynomials, pa of x times pb of x. To do this, we'll perform a multi-stage process. We'll take a set of points, τ1 through τk, and we'll evaluate our polynomials, pa and pb, in all these points. Then we'll compute products of numbers, pa of τ1 times pb of τ1, and up to the last product. And then we'll interpolate. We know the points, we know the values of the product of polynomials on these points, and then we can reconstruct by interpolating the polynomial pa times pb. But there is one detail here to note. When we take product of two polynomials, each of them of degree k minus 1, the product itself has degree which is the sum of the degrees of the polynomials. So the degree of this polynomial is 2k minus 2. And to be able to uniquely reconstruct this polynomial, we need its values not in k points, but in 2k minus 1 points. So actually, we need to enlarge our set to 2k minus 1 points, and we need to compute pa and pb for all these points, just so that we have enough points at which we'll know the product of pa and pb, so that we can reconstruct uniquely the polynomial by its values. So this is our final scheme. We'll take enough points, they will all be integers, we'll calculate all these values, and recall that our polynomials pa and pb are actually polynomials with integer coefficients. So all these guys are integers as well. Then all these guys are integers. And computing the coefficients of products can be done by computing results of linear combinations with rational coefficients. And these rational numbers, Cij, they are fixed as soon as tO's are fixed. So now let's take a concrete set of tO's, say from 0 to 2k minus 1, just consecutive integers. So recall that k is fixed, and recall that our polynomials like pa of x are polynomials of degree k minus 1, where the coefficients of these polynomials have n over k bits. Now if we compute pa for a value of x which belongs to this set, the number of bits in x is constant, and all these numbers can be actually pre-computed, so these are just constants for us. So we are taking a linear combination of these guys, of aj's, where the coefficients are already pre-computed constants. Multiplying a given integer by a constant takes linear time, and then summing up a constant number of such things is also linear. So computing this value takes linear time. Thus we can do this part of our algorithm in time big O of n. What is the number of bits in the result? So what is the number of bits in each of these numbers? It doesn't exceed n over k plus constant number of bits, where this constant of course depends on k, but k is fixed. So now when we are computing the products, we need to compute 2k minus 1 products of numbers that fit into n over k plus constant number of bits, and we can do it recursively with our algorithm in the time which is t of n over k plus big O of n. Just as in Karasova-Hoffman, at one step of the algorithm, we needed to compute the product of numbers that didn't have n over 2 bits exactly, but rather n over 2 plus 1 bit. Now here we have n over k plus constant number of bits, and still we can get rid of this plus constant in time which is linear on n. So in the end, we are performing 2k minus 1 multiplications. Each of them takes time t of n over k plus big O of n. And so finally, let's speak of the last step of interpolation here. To get coefficients of this polynomial, we need to compute linear combinations with given fixed rational coefficients of the values of this polynomial on given set of points. Each of these guys fits into 2n over k plus constant number of bits, and to compute linear combination of these kind of numbers, we need time which is big O of n again. So in computation of this polynomial, in interpolation, we need to compute 2k minus 1 coefficient. Computation takes big O of n time, but as k is fixed again, everything fits into big O of n time. Now, after we have computed all the coefficients of this polynomial, let them be c0 through c 2k minus 1, the last thing that we need to do is to multiply each of the coefficients by 2 to the power of n over k, and multiplying by the power of 2 essentially means shifting these binary numbers. So the last number c 2k minus 1 would be shifted by this number of bits, and then we just add up all the resulting numbers to get the actual value of the polynomial in the point 2 to the power of n over k. So then the computation of a polynomial at a point takes time which is big O of n. All of that is possible because k is fixed here, and thus all such things that they are linear on n. So in the end, our process involved 2k minus 1 recursive computations of products of numbers of length of n over k, plus some linear work to do, and the master theorem would tell us that t of n is big O of n to the power of logarithm base k 2k minus 1. So for k equal to 2, this gives us exactly the bound of Karatsuba and Hoffman, and for greater k, this logarithm actually can be made closer and closer to 1, as close as we want. So in the end, we can get the following statement. For arbitrary epsilon greater than 0, we can choose k such that t of n will be big O of n to the power of 1 plus epsilon. We can get this power as close to 1 as we like. But we see that, of course, with larger k, we'll have larger number of machinery to carry out, and thus the constant in this big O would be quite unpleasant. So for large k, this algorithm remains theoretical, not practical. But the idea that we can convert the product of two numbers, the problem of computing this product, into the problem of computing the interpolation of a polynomial and computing the product of two polynomials is very, very influential. And later, many of the improvements that were made in number multiplication relied upon this idea of parallelism between multiplying numbers and multiplying polynomials.